You know, in engineering, especially when you're talking about something as wild as rocket science, there's this constant tug of war between getting the best possible performance and just making something that works without breaking. But every now and then, the most elegant, the most reliable, and honestly, the most life-saving solution is also the simplest. So today, we're going to dive into one of the most fundamental designs in all of rocketry, the pressure-fed engine.
Okay, let's just start with a really basic question. If I told you right now, go build a rocket engine, what's the most straightforward, no-frills way you could possibly make it work? Let's just forget about peak efficiency for a second. We're talking pure, simple function. And that question right there leads us straight to the pressure-fed engine. And believe it or not, the core idea is probably something you've used 1,000 times. It's basically a giant, powerful aerosol can. Seriously. That simple idea of using a pressurized gas to shove a liquid out of a nozzle, that's the brilliant concept behind this entire class of rocket engines. So how do you scale up a spray can to a rocket? Well, a pressure-fed engine has a separate tank filled with a high-pressure gas, usually something that won't react, like helium, and its only job is to literally squeeze the fuel and oxidizer out of their own tanks. This forces them down the pipes into the combustion chamber where they ignite and, boom, you get thrust. The key here is what's missing. There are no crazy complex pumps or turbines spinning at terrifying speeds. It's just the clean, elegant force of pressure doing all the work. And when you look at a diagram like this, what's so cool is just how clean it is. You've got your gas tank up top, the pressure in. A valve opens and that gas flows into the fuel and oxidizer tanks. All that new pressure has to go somewhere, right? So it pushes the propellants out, through their own lines, past a couple valves, and straight into the combustion chamber. It's just an incredibly direct and robust system.
So that's the basic idea. Now let's walk through what actually happens when you fire one of these things up. And you might be surprised by just how few steps there are. The startup sequence is it's beautifully simple. First, a valve opens and lets that helium pressure into the propellant tanks. Step 2, the main engine valves open and the now pressurized fuel and oxidizer start flowing into the chamber. And third, ignition. Now, if the propellants are hypergolic, meaning they ignite automatically the second they touch, the engine just roars to life. If not, a simple little igniter gives it a spark. That's it. It's that simple. This amazing simplicity also unlocks one of the engine's greatest strengths, the ability to restart. Think about it. If you need to stop the engine and then fire it up again later to, say, fine-tune your orbit, no problem at all. You just close the propellant valves to stop the flow and then open them up again whenever you need another push. This on-demand on-off switch is absolutely vital for maneuvering in space. Now, this whole idea of simplicity isn't just a neat design choice. It actually represents a huge fork in the road in rocket engineering. Because the alternative? Well, the alternative is a lot more complicated. And wow, this slide really says it all, doesn't it? On the left, you've got that clean, logical flow of our pressure-fed engine. On the right, that is the mind-bogglingly complex diagram for the Space Shuttle's main engine, the RS-25. It's an absolute engineering marvel, but it's a terrifying maze of turbopumps, preburners, and plumbing. All of that complexity makes our simple pressure-fed system look like a toy in comparison. And this, right here, is the central trade-off. Pressure-fed engines are simple, they're super reliable, and they're easy to restart. But what's the catch? Well, they're heavy, and they can't generate the insane pressures you need for maximum power. Pump-fed engines, on the other hand, are unbelievably powerful and efficient, but they get there by using extremely complex and high-stress turbopumps, which are, famous points of failure. Okay, so where is this simple, reliable design not just a good choice, but the perfect choice? Well, imagine you're hundreds of thousands of miles from home, and your life literally depends on an engine firing exactly when it's supposed to. You don't want the fancy one, you want the sure thing. And just look at the resume for pressure-fed engines. It's legendary. These were the engines that NASA trusted to land the Apollo astronauts on the moon, and more importantly, to lift them off again to come home. They were used on the main Apollo service module, on the Space Shuttle's delicate maneuvering engines, and even today on SpaceX's Dragon capsule for both attitude control and its life-saving launch escape system. Let's just zoom in on a classic example. One of the Space Shuttle's orbital maneuvering system pods, the OMS pod. This pressure-fed workhorse did all the heavy lifting in orbit. The final push to get there, all the big orbital adjustments, and of course, the critical deorbit burn to come home. It was so reliable it could be reused for up to 100 missions.
And as the source material for this explainer puts it, when you're talking about the small thrusters that control a spacecraft's orientation and the bigger engines that shift its orbit, the designs are almost universally pressure-fed. Because out there, in the vacuum of space, you can't just call a mechanic. Reliability isn't just important, it's everything. So the big question is, if this design is so rock solid and so trusted, why isn't it used for everything? Why don't we see massive pressure-fed engines lifting rockets off the launch pad?
And the answer comes down to a really simple, unavoidable law of physics. If you want high thrust, you need high pressure in your combustion chamber. And in a pressure-fed system, that means your propellant tanks have to be at an even higher pressure. To contain all that force, your tanks need to have thick, strong walls. And thick walls are very, very heavy. You can see the problem right here. As you try to dial up the engine pressure to get more power, the weight of the tanks you need to feed that engine just skyrockets. And in the world of rocketry, weight is the ultimate enemy. Every extra pound of tank is one less pound of satellite or astronaut you can get to orbit.
And that, right there, is the ultimate trade-off. That weight penalty from the high-pressure tanks eventually gets so huge that it makes these engines totally impractical for the giant first-stage boosters that have to fight their way through Earth's gravity. For that brutal job, you really do need the raw, lightweight power of a complex pump-fed engine.
So this leaves us with a final thought, one that really gets to the heart of space exploration. As we design the next generation of spacecraft, the landers, the deep space vehicles, this fundamental choice is always there. It's this constant balancing act between the raw power you need to leave a planet and the clever simplicity you need to maneuver and survive once you're out there. It's the simple spray can versus the complex machine, a trade-off that's going to keep defining our journey into the cosmos.